Hey guys, welcome to part 2 of Force and Newton's Laws of Motion's notes. Today we're looking at Newton's second and third laws, as well as talking about some free body diagrams. So, Newton's second law is that force is equal to mass times acceleration, which is what I just said there, is the product of the mass of the object and the acceleration that it is experiencing. But when mass is in kilograms and acceleration is in meters per second squared, we already talked about that the unit of force is measured in newtons. That is our standard SI, scientific instrumental units. For force, it is equal to the force required to accelerate 1 kilogram of mass, 1 meter per second per second. So we can go through and kind of do some calculations now with this. We've got a formula that relates to a piece of information together with a third. So if we're trying to calculate how much force is needed to accelerate a 1,400 kilogram car 2 meters per second, we're going to start by just writing down our formula. Force is mass times acceleration, FMA. We're just going to fill in the numbers then the units that we're given. So we're given our force, we're given our mass and an acceleration as seen. So we're just going to multiply those together to solve for the unknown thing. So in this case, 2,800 newtons is what will be required in order to accelerate that 1,400 kilogram car by 2 meters per second squared. For this next one, we can kind of look at relationships between different, between the mass, the force, and the acceleration. We can see that our mass and acceleration are directly proportional to our force. So that means just we can multiply them together to get our other. So we can kind of look at how those relate to each other. If we doubled our force without changing our mass, we know that's going to also double our acceleration. Or vice versa. If we double our acceleration without changing the mass, that's going to double our force. If we kept our force doubled, but we kept our acceleration the same, what's going to happen to my mass? Well, in order for us to have a force twice as big as what we originally started with, look back up the top of our table, without changing our acceleration, that would mean we would have to do what to our mass? Our mass. In this case, in order to multiply those together, we'd have to also double our mass. So if either of the two, mass or acceleration, remain the same and our force changes, we know that that's going to have to lead to a change in that other thing. Here, if we kept our force our force the same, and our mass was now 5 kilograms, our acceleration, again, since we have to multiply together, they have to be inverses of each other. So our acceleration here for this next row would have to be 2 meters per second. And for the last one, if our mass was 1 and our acceleration was 10, again, our force would just be 10. They multiply together to be 10. But in general, again, those last two sentences down here, if the mass remains constant, doubling the acceleration will be doubling the force. And if force remains constant, doubling the mass would then cut the acceleration in half. So if that force is the thing that remains the same, any kind of manipulation of either of those two things on the same side with mass and acceleration, if one doubles, the other one has to be cut in half in order to still multiply together to get that same thing. So just something to keep in mind. Newton's second law proves that different masses accelerate to the Earth at the same rate, but with different forces. So we know, the old thing where if we drop a feather and a rock at the same time in the exact same space, they would fall identically. Kind of the same thing for our bigger rock and a small rock, even though they're the same thing, the same shape, the same composition. There's people who still think that because they fall at the same rate, they're acted on by the same force, which is not true. In this case, because our acceleration is the same, they accelerate at the same rate, 9.8 meters per second squared, the force acting on them does depend on the size and the mass of that object. We can see here this big rock has a mass of 10 kilograms, while the small rock has a mass of 1 kilogram. They both accelerate at the same rate due to gravity, because that's the only thing acting on it. But the force that gravity is actually acting on, because force depends on your mass and your acceleration, the force due to gravity is 98 newtons on the big rock, while only 9.8 newtons on the small rock. So again, kind of be careful of how you're phrasing things. The force acting on them is the same source. They're both acted on by the gravitational pull, but the acceleration being the same does not mean that the magnitude of those forces are the same. All right, so a little check for understanding. If we're going to just do a couple example problems here again, what acceleration will result in a 12 Newton net force applied to a 3 kilogram object? Again, we're going to set up our formula. Force is mass times acceleration, so 12 equals 3 times A. So we could work backwards to figure out that 4 meters per second squared would be our acceleration. A net force of 16 Newton causes a mass to accelerate at a rate of 5 meters per second squared. Determine the mass, again, FMA, so our 16 equals m times 5. So we divide by 5 on both sides. 16 divided by 5 is 3.2. How much force is needed to accelerate a 66 kilogram skier 1 meter per second squared? So here we got a skier person. So 66 kilograms, 1 meter per second. Multiply those together to get the force of 66 newtons. Last one. What is the force on a 1,000 kilogram elevator that is falling freely at 9.8 meters per second? So here a little bit tricky because we don't know, like it says, it gives us the acceleration. Actually, it's not really that tricky. It looks confusing because it says falling freely, but it tells us our mass, 1,000 kilograms. It tells us our acceleration, 9.8 meters per second squared. So we multiply those two together to get 9,800 newtons. All right, shifting a little bit, talking about forces more in general here. We've got force. We talked about that's cause and acceleration. We talked about different types of friction, different sources of friction, but these are different kinds of forces as well. We have different sources of force. Source of force, fun. We know that force is a push or pull that causes a change in the object of the motion. We have gravity, we have electrical force, we have magnetism, and we have friction. Those are all different kinds of forces. When we're looking at analyzing net forces working on an object, it's a lot easier sometimes to simplify the problem down into just a little ball or a little rectangle, which we call free body diagrams. We kind of remove it from the picture that we're looking at and looking at specifically just how are the forces acting on that body. So we have that, it looks like this, where we start looking at more specifically some of these different kinds of forces and which directions they're acting in. So gravity is our most common one. We know gravity always acts downward. So we know that that's always going to be the case. If we're looking down, F, so just capital F, and then the lowercase g-r-a-v, subscript, just saying the force due to gravity is 9.8 meters per second on Earth. We know that, m times mass times gravity is our force due to gravity based on the second law that we just looked at. Some of these other forces here are normal force. It's a little hard to kind of picture, but it's always the force that's pushing up against a solid surface. So it's always a perpendicular force to whatever direction our object is moving. So if I am, walking horizontally across the floor, the normal force is pushing up against me. So it's kind of, right now I'm sitting in my chair. The normal force is what's keeping me from falling through the chair. My butt is pushing down on the chair with, due to the force of gravity pulling on it. The normal force is pushing back up against it to keep me at rest. That's what a normal force is. Friction, we already talked about that. We talked about friction always being kind of a competing force. It's always impeding our movement. It always acts in the opposite direction of whichever way our object is trying to move, in which case we call that our applied push or pull. So just APP, applied push or pull, is that force. So that's just what we abbreviate it down to, F of APP. And that's, again, either pushing our object or pulling our object in a certain direction. That's just always our forward moving force. And this kind of orientation is usually how we have it. We always just assume it's moving to the right, friction always moving to the left. But again, this could be moving to the right or moving to the left, and this could be moving to the right. It depends on which direction we're trying to push our object. The other one that we'll see occasionally is tension, and that's when we have something hanging. So like if I don't really have anything to hang from, I don't know, if we're looking at, can't reach over here. If I had like a string or a rope or any kind of chain or anything like that, if I'm hanging from something, that force that's keeping it from falling down, again, it's an upward force. Tension is usually an upward force unless we're like pulling tug of rope to go horizontally. Again, it's just a force that always acts upwards, and that's another different type of force. So when we're looking at our free body diagrams, we're trying to figure out what's the net force of that object. If there's an unbalanced force, that's going to be the sum of all the different forces, and we can describe it we have to describe it in both its magnitude and its direction. So if we go through some of these, looking at this first example here, we've got 1,200 newtons of tension pulling up on the object. We've got gravity pulling down with 800 newtons of force. So we would say the net force, F net, is 400 newtons up. And that's pretty much it. I mean, we can go through some other examples of it. Here, my air resistance, F air, that's air resistance. That's just something that's always, again, pushing up against it. If you were falling, the air would try and stop you from falling. We have a net force of 200 newtons down because gravity is pulling stronger than the air resistance that it's experiencing. Here, my normal force and my gravity balance out, meaning it's just staying on the tabletop, it's staying on the counter, whatever the case may be. So our forces vertically cancel out. I just have a 20 Newton frictional force resisting it. So we would say our net force is 20 newtons to the left. All right, so something like this problem here, I could put a context to it if we wanted to. This is the last little thing here. With this, we have 3 dogs fighting over a bone. We've got the biggest dog pulling right at 35 newtons of force, a kind of a medium dog pulling to the left at 20 newtons of force. They're fighting against each other. And then you've got this scrappier little dog that's 15 newtons of force pulling upward with it. Now, if we're looking at what the path the bone would follow, what's going to happen as they play tug of war with the bone, we have to look at how those forces all balance out. And it's not going to be perfectly in one direction or the other. We don't have kind of offsetting ones. We have combining vectors, where if we look at how our forces interact with each other, we can kind of boil this down into what's the net horizontal force, what's the net vertical force, and look at how those interact with each other. So we can see the two dogs that are pulling directly against each other, 20 newtons left and 35 newtons right. That tells me that I've got a net horizontal force of 15 newtons, right? Because 35 minus 20 is going to be 15 newtons, which means if I've got 15 newtons pulling up, 15 newtons pulling right, the end vector is going to be 45 degrees this way, and I've got to do a little right triangle. Ooh, that's a horrible right triangle to figure out what that's going to be, because I've got 15, and actually I should be. There we go. 15 up, 15 over. So this is going to be 15 square root of 2 newtons. And that's going to be at 45 degrees from the horizontal. All right, continuing along. For Newton's third law of motion. Newton's third law states that for every action, there is an equal and opposite reaction. So anytime two objects interact with each other, they exert forces upon each other, whether it's two objects in motion interacting with each other, whether it's just you sitting on a chair and the chair pushing back up against you. That would be like gravitational force and normal force. You have that kind of exchange of forces. They're equal and they're opposite. When two forces, there are two forces resulting from this interaction, a force on the chair and a force on the body. We call them the action and the reaction forces. Again, that doesn't necessarily mean that there's no net force acting on our objects. It just means that when they interact with each other, one is acting upon the other is reacting back off of it. So if we imagine a fish swimming in water, as it kind of flaps its fins and kind of, does its thing, it's pushing the water backwards, and in turn, the water is pushing the fish forward. There's the action of pushing the water back. There's the reaction of the water pushing forward. The size of the force is equal to the size of the force put into it, so the net force action. So how much force is added by the fish, flapping its tail or flapping its fin to push that water back away from it. That water is going to push back with exactly the same force, which is what causes that change in direction. Same kind of thing happens when we talk about birds flying. A bird is pushing air down with its wings, and the air is being pushed back up against it with the third law of motion, which is why that works that way. Again, the size of the force put into the reaction is the size of the force given back out. So if the bird flaps its wings really big wings and really hard wing flaps is putting a lot more force into that reaction, so the bird is going to fly up a lot higher, which is why the faster that you flap the wings with, or the harder that you flap the wings with, the higher you're going to go as a result. There's a nice little GIF. Another example here, when you swing a baseball bat and you hit the ball, the bat acts on the ball, but the ball does push back against it. Now here, you don't usually see, whoops. Now, it's hard to understand that there is still a pushback against the ball because I have so much more mass and so much more velocity of the bat. Well, not necessarily velocity, but so much more mass with the bat than the ball that you don't really feel or see that reaction very much. Because the mass of the ball doesn't have a huge impact on the bat itself. It's mostly the bat continuing forward. But if you've played baseball, if you've played softball, you know that when you swing, you can still feel you make contact with it. And that little bit of a feel for it, especially depending on where it hits on the barrel, you can feel that feedback of the ball pushing against the bat as well as the bat pushing on the ball. Same thing for a car, the way it moves. The car, it's kind of a weird thing to think about, but the way that cars move, we know that their wheels turn. But really what's happening is not necessarily that, they're just being propelled forward. The wheels push against the road to push the road backwards. And then as a result, the car is pushed forward because you can't push the road backwards. It's kind of a weird thing to think about the way the cars work, but that's one way of actually visualizing it. As the wheels turn, it's pushing the road backwards against it, so it's being pushed forward against, or along the road. Last one here, a rocket launch. Pretty self-explanatory one here. The way that it works, my action is going to be the gas burning and accelerating and flowing out of the nozzle. And because that hot air and that hot gas is pushed down against the inside of the tube and down at the bottom, there's a lot of force, a lot of motion going out of the gases, out of the nozzle of the rocket ship, the bottom of the engine. So all of that gas pushing down against the ground ends up accelerating the rocket up forward into infinity. That's all we got for Chapter 3. That's the end of the third law. That's all I got for you guys today. So as always, if you have any questions, concerns, thoughts, ideas, hopes, or dreams, make sure you guys are reaching out and letting me know. If not, have a fantastic day, and I will see you guys soon.